Good morning, everybody. That's it? Good morning, everybody. I know it's been a long week. How's build going? Yeah? Well, okay. That was pretty good. It's great. It's the best build so far this year, I'd say. So welcome to Inside Microsoft Azure Data Center Hardware and Software Architecture. My name is Russinovich. I'm the Chief Technology Officer of Azure. I've been in Azure for 8 years and seen a lot of change, going from something relatively small that nobody knew anything about to now a cloud platform that spans the world. What I'm going to do for the next 75 minutes is share with you an inside look at our data centers, both the physical aspect of our data centers as well as the logical aspect of our data centers. And I'll be highlighting, as I go through the architecture, some of the innovations that we've been working on and some of the ones that are coming, some of the ones that we've released recently, and where we're going with these innovations. The breakdown of the agenda here is I'll start with a look at the data centers themselves, how they're constructed, how we organize them within a geography, how we connect them on the network. Then I'll go into the physical network a little more deeply, show you how we wire within the data center itself and across data centers, get into some of the logical networking services, some of the cool enhancements that we've just put in recently there. Then I'll take you down a tour, little history of Azure servers as they've evolved over time. And this is kind of interesting, from the day that I started in Azure, what the servers looked like then, to what some of the servers that we've got now deployed in our data center. I'll also talk a little bit about the hardware innovation that we've got with server design and highlight some of the cool applications that we can build on top of that. I'll then transition to the compute service or services, and I'll talk about the compute architecture, and then talk about some of the things we're doing with containers and serverless and microservices. I'll talk then about storage, the logical topology architecture of storage, a cool change that we're rolling out right now with a change in the architecture to that will provide some really cool performance enhancements, and then talk about some of the forward-looking work we're doing with storage technologies to make it more cost efficient. And then I'll switch to a little bit lower layer, the hypervisor and the operating system, tell you about what we're doing to keep the operating system more available as we roll out patches. And then I'll conclude with a look at quantum computing and what we're doing there. So it's going to be a tight agenda. I'm going to be moving very quickly through this, and I apologize, but there's just so much to show, and I have to admit that this talk is about 75 slides, which in 75 minutes is a little tight. But it started out as 115, so there's a bunch of things that unfortunately I don't have time to show you, but I'm trying to squeeze as much coolness in as I possibly can. So let's start with a look at the data centers themselves. And I'll first talk about the way that we organize our data centers. We start by defining what's called a geography, and a geography is defined as a geopolitical boundary where most of the customers within that boundary are comfortable having their data anywhere within that, from a regulatory perspective, from a compliance perspective, or just a cultural perspective of wanting their data within that boundary. More and more, these are becoming countries. And so you can see as we've rolled out our geo expansion, we've gone into places like France and made that a geo. We've gone into places like UK and Australia, and those are geos. Then we define regions within geographies. And for every geography, we have at least 2 regions. We define a region as a latency boundary. So any data centers within that region, and many of our regions have multiple data centers, have to be within 2 milliseconds round trip latency of each other, less than 2 milliseconds. So our target is less, but we guarantee 2 or less. And we do that so that you can build an application that can replicate data within that region. Then we also have this architecture where we pair regions together so that you can do a disaster recovery failover from one region to another. And we move those data centers as far as those regions as far apart as we can within the geography so that they're isolated from large-scale natural disasters like hurricanes, floods, earthquakes. Typically, that's hundreds of miles apart, which means that they're too far for synchronous replication to achieve high availability. But they're far enough apart so that these large-scale disasters you can fail away from, and potentially fail away from in a catastrophic scenario, lose a little bit of data as you're moving across. For high availability within a region, we're just started to introduce availability zones. And availability zones are multiple independent data center facilities. They're isolated from one another, both in some distance between each other, as well as they each have independent power, they each have independent connections to our network backbone. They each have independent water supplies, so they're isolated from having any correlated failures from a physical perspective between each other. And of course, because they're separate buildings, they're also physically isolated with respect to things like fires and floods within the data centers themselves. Our inter-AZ latency diameter, again, because they're in a region, is going to be in that 2 millisecond boundary. And whenever we go into one of these regions with availability zones, and our plan is to roll these out more and more, you can see that we've got I'll show you, we've got a couple in that are G8 and a few in preview, is to have at least 3 in each region. And the reason we go in with 3 versus 2 is that you can then replicate data statefully and achieve quorum. So where you have 2 out of the 3 responding and acting to a write, you know that you can then lose one of the copies and still not lose any data. We do this logical to physical mapping. So if you take a look at the region, we might have more than 3 physical AZs, like this example here. But what we do then is logically map a customer subscription, the AZs that are projected to them, to those physical AZs underneath them. And we do that so that we can shape capacity and make sure that customers can continue to expand in the AZs that they've been assigned. We can bring new subscriptions, new customers into that region, and then make available new data centers as additional AZs that are visible to them that they can grow into as well. So there's just an example of a little mapping. Here's an example of what we've got going on so far. Like I mentioned, we've got a couple in GA, we've got a few in preview, and then we have a lot of services that are zone optimized, meaning that they've been specially designed to work with this zone architecture. If you take a look at this list, you'll realize that it's the fundamental building blocks of the cloud infrastructure that are the ones that are zone specific, that you can place within a zone. And that is so that you can build a zone resilient service on top of them. So our higher level services, like you can see there, Azure SQL Database and zone redundant storage, those themselves build on those fundamental building blocks of placing a virtual machine within one zone, placing an IP address with one zone, and then that way they can do that across the 3 zones and then replicate across those virtual machines, across those networks, and have this availability such that a zone can fail and they can continue to serve writes. 2 zones can fail and they can continue to serve reads. And then you can see here some of the distance between the zones in our French region, France. There you can see Paris there faintly towards the top middle. And you can see there 2 zones south of Paris and 1 zone north of Paris, connecting those 2 within that 2 millisecond latency diameter. Now to show some cool pictures, I like to see real stuff, and so I like to go visit our physical data centers. And the one that's closest to here is the Quincy data center that's out by the Columbia River. This is a picture of some of our data centers there. Each one of those facilities is 8 megawatts in size, so that's a total of 64 megawatts you're looking at there. The region's even larger than that. Here's another shot of additional data centers in that Quincy region. We build out over there because there's a great supply of hydroelectric power there, and so we're not the only ones that build out in Quincy. Lots of land, lots of power available there. Here's Cheyenne, another place that's great for creating a very large region, and you can see there the same data center architecture. There are 8 megawatt colos, 4 of them down at the bottom, and then there's a facility over on the right side, and then a clearing space for new ones. And this is Dublin, Ireland, another place where we've been expanding. There's different data center architectures shown in this picture. You can see over on the right side a bunch of data centers there, and one down towards the bottom. And if you look really closely, you can see the Guinness Brewery. Just kidding, you can't see that there. Here's Amsterdam, and you can see we're expanding massively in Amsterdam. There's a large area being cleared for a bunch of data centers there. That building over on the left side, that looks like it might be a data center. It's actually not. Does anybody know what that is? It's a greenhouse, and because it's the Netherlands, you have a 50-50 chance of guessing what they're growing in there. Yeah, tomatoes. That's it. So here's another shot of Amsterdam with more expansion there for data centers, a different view. You can see wind there, powered by wind farms. And then here's a look inside one of our data centers, Cheyenne. Just to avoid any confusion, the servers do not slope inside the data centers as it looks like in this picture. So speaking of natural energy, we've got a commitment to sustainability at Microsoft all up. And our data centers are no exception. We've been carbon neutral across our data center footprint since 2012. This year, we crossed the 50% natural energy threshold for our data centers. Our goal is to get to 60% by 2020, and of course, our long-term goal is to be 100% powered by wind, solar, and hydropower. And you can see some of the different kinds of energies in the different regions there that we're using. We just signed the largest solar corporate deal in history in the United States in Virginia for 275 megawatts of solar power there, just as an example of us procuring energy for the global expansion of our cloud. We're also working on trying to make our data centers more efficient in the way that they consume energy, even taking a look at very radical types of designs for the data center. As you know, data centers are powered by utility energy, utility electricity that comes into those data centers. And one of the things we realized as we looked at that architecture, first of all, utility power is not that reliable. So we have to have generators there to back up the utility power. But second, there's a whole lot of switches and transformers on the way from utility power into the data centers, into the servers. So every time you have one go through one of those devices, you lose a little bit of energy in the transition. So there's a significant amount of energy loss as you get down to that servers. And there's also, for any one of those switches, that's another potential single point of failure on the way to the servers. So we've been looking at using fuel cell technology, natural gas powered fuel cells. Natural gas, by the way, if you take a look at the reliability of it, it's 6 nines or higher as compared to utility power, which is significantly lower than that. So we get higher reliability for the utility natural gas coming into the data centers. Of course, we'd have redundant connections into them. But then there's no switches. The electricity is generated right there next to the servers. So there's a direct conduit from the energy source into the servers. And we expect that we can save about 50% in energy reliability and efficiency. So that's a look at our data centers. Let me talk about our InterDC network now and what that architecture looks like. Here you can see 2 regions, A and B, and then you can see the connections out to the rest of the world, out to customers, enterprises, and enterprise VPN connections through ExpressRoute. That's all connected through our WAN, and we've got within regions, regional networks. You can see the types of services that we deliver on this network, from our DC hardware with our NICs that I'll talk a little bit more about, to the services we deliver within a region and across regions, to inter-region data center network, like DC networks, regional networks, optical modules that we use for optical switching within a region, our software WAN, the subsea cables that we've been deploying, and our internet peering sites. Speaking of that physical topology and internet peering sites, this is a look at the current state of our dark fiber backbone. So all of the traffic between our regions, between data centers, flows over our own fiber, either leased or completely owned by us. We've been investing huge amounts of capital infrastructure in building out the worldwide WAN. And last year in the fall, we announced, for example, the GA of undersea cable crossing the Atlantic called Maria that goes from Bilbao, Spain to Virginia, the first cable crossing at a different place than going from England to New Jersey, New York, a project with Facebook and Telsus, which delivers 160 terabits of capacity, making it one of the largest subsea cables ever deployed. And we've got another 2 projects that are underway crossing the Pacific as well. If you take a look within their regional network architecture, so this is the connection between data centers in a region. Like I mentioned, many of our regions consist of more than one data center, some of them up to a dozen or more data centers. And we connect them with something called these RNGs, regional network gateways, you can see. They're optically driven, so our custom optical technology to connect these different networks together. They're space and power protected, so we've got redundancy. You can see there's 2 RNG stations whenever we have one of these connections between data centers. They're physically far separated in land by several kilometers. They've got independent power and utility and water, so just like our data centers, they're protected with redundancy purposes, so we don't lose a region if one of these goes down. And then we build them in what are called t-shirt sizes. So depending on how big we expect the region to get, we can start with the small one We can expand it to medium size, or we can start with a large one. And kind of not surprisingly, as the demand for cloud continues to grow and some of our regions are getting bigger and bigger, we're realizing that we're going to probably need to XL, and then XXL, and then XXXL at some point. But that's the state of our RNGs as they connect together. The network is incredibly complicated, and one of the easiest ways to take a cloud service offline is to screw up the network. Advertise the wrong route, for example. And so whenever we add hardware, switches to our network, or new data centers, bring them online and add them into the RNGs, whenever we build out a new cluster of servers in our data center and bring those online with new top-of-rack routers, that's a reconfiguration of the network to add those servers to the route and make them visible to the rest of the world. Very complex programming. In many cases, programming like that, a small error can take down a whole region by black holing certain IP ranges. So what we've done is build our own network test service called CrystalNet. We published a paper on this in SOSPI, the Symposium on Operating System Principles, in the fall, where you can go read more about it. But this is a very accurate representation of our entire network configuration across the world. We run it in about 70 virtual machines. It reads the real configuration off our network, and then we can simulate changes and see what would happen on that. Once we've verified that the change does not impact any of the routes and does what it's supposed to do, then we can export that change and apply it. And so there's no human involvement after we've verified that the change actually works. We can even connect physical devices to this virtual simulation directly, so we can also then see how they would react and how they would interact as points along this whole network architecture. So this is, you can see we've spent over 12 million core hours in emulating our network changes over the last 6 months. And just as our networks get bigger and bigger, this is going to become something we rely on more and more. So that's a look at physical networking. Let me switch to logical networking now. And logical networking in the cloud is based on something called software-defined networking, or SDN. If you take a look at traditional IT networking, it's generally been come in the form of hardware appliances. And those hardware appliances have a bunch of different services built into them, from high-level abstractions and management APIs down to the data plane where the network traffic actually flows through the appliance itself. And the control plane is where the management APIs take and transfer those APIs into low-level commands to configure the routes on the switches. And so all of this is built in. And one of the things that we found out very early in the development of Azure, as our networks got bigger and bigger and they were growing so dynamically, is that these, to support the kind of traffic we needed, were becoming very expensive. They also were single points of failure. Or at least, if you wanted to avoid a single point of failure, you had to get 2 of them, and that was very expensive as well. So we realized very quickly that this architecture was a dead end for us from a cost and reliability perspective and a scaling perspective. So just like many others, we embarked on creating software-defined network for our data centers. In our case, if you take a look at the layers, at the very top, the management APIs to Azure are in the form of Azure Resource Manager APIs, ARM APIs. You call into ARM, and then you end up in a controller that is taking those ARM APIs, like create a new virtual network, give it these subnets, and add these virtual machines to it, and it takes those commands and takes those and configures the software-defined network, the various controllers that implement things like public IP addresses and virtual networks. And then those themselves go and program the switches, and these aren't appliances, these are the servers themselves. The switches are implemented in software on the servers. So it's a very distributed network. These 3 layers mean we can scale out each layer independently to grow. It's using standard cloud-native type of resilience architectures, so we can tolerate large-scale failures even of a whole AZ and still not have these software-defined networks go down. And then, because the switches are in the servers, they're just part of the server price, and that also scales with the scale of our servers. Just a little deeper dive in the way that software-defined networking looks. In the case of its management, the resource provider, the controllers like the regional network manager, the directory service, the software load balancer controller. The way that they interact with our servers is by orchestrating communication with the compute resource provider. So the way that network doesn't make any sense without compute to use the network. So it's really compute that kind of drives the implementation of a network, saying, I'm going to place a virtual machine on this server. This virtual machine needs to be on this subnet of this virtual network, and it needs to have this public IP address. So that dance happens with the compute resource provider talking to its own agent on the server, the network resource provider then getting commands or taking commands and sending them down to its agents down on the server to program the virtual filtering platform, the switch there you see on the lower right. That is that switch that I was talking about earlier. That bottom layer of those physical appliances now distributed into those servers. When we started with Azure, we implemented those switches purely in software on the servers. And if you take a look at what those switches do, it's a bunch of different operations. They apply network ACLs, they expose public IP addresses with load balancing, they implement virtual networks with subnets and routes configured on those subnets. And so all of that is implemented in different layers of rules that were run in the software on those servers. About 4 or 5 years ago, we went, as you'll see, from 1 gigabit networking on the servers to 10 gigabit networking. And we started to see significant CPU consumption by that logic for that switch, software-defined switch on those CPUs. We realized that not only were we burning expensive general-purpose CPU cores with the software-defined networking, we were also introducing latency to the network by all that packet processing in those servers. And if we looked forward, we saw 40 gigabit network coming, 50, and then 100 gigabit network coming. We project that out, and you're burning a whole bunch of very expensive cores and impacting latency significantly by doing all of that on the CPUs. So we took a different approach with field programmable gate arrays. Those of you that were billed last year saw me give a presentation, a deep dive on FPGAs. I don't have time to do that here, but effectively, if you take a look at the spectrum of hardware, it goes from general purpose processors like GPUs and CPUs, and down to ASICs, which are custom hard-coded pieces of silicon with algorithms basically embedded in them. So very fixed function, but once you're in fixed function, you're very low cost, and you're very low power. And you also get great performance because it's just been optimized for that particular algorithm. On the general purpose side, you can do anything on it. But that's also its problem. It's not optimized for anything, so they consume a ton of power, and they're not necessarily the most efficient way to run the algorithm. In the middle are FPGAs. FPGAs have programmability that's somewhat like the general purpose CPUs. They're massively parallel, and they're implemented as programmable hardware switches. So they look a little bit like programmable ASICs. And what that means is you can put algorithms on it and map them to this programmable hardware fabric and get close to ASIC type performance, draw a lot less power than you would with the general purpose CPU. So we started putting FPGAs in every single one of our servers, and then over the last year and a half or so, we started to light up a feature called accelerated networking in Azure. Accelerated networking takes advantage of these FPGAs by completely bypassing the servers themselves on the data flows. You can see that on the left side is what we used to do with the virtual switch on the servers, talking to the network adapters. And on the right side, you can see the FPGAs there are sitting in line on the servers with the NEC, with the network adapter. So that means that the data flows, the data traffic comes out of a virtual machine. It's mapped, the NIC is mapped into the virtual machine virtually through SROV. And now the network stack in the virtual machine can send packets basically directly into the FPGA, which then implements our software-defined networking rules, does filtering, rules, encap, decaps, and then sends it out through the network adapter to the network. Now, we got amazing performance gains and bandwidth gains, plus a lot lower CPU usage when we went to these FPGAs and accelerated networking is turned on. But recently, we've been deploying something called DPDK into our Linux virtual machine images. And with DPDK, this is a software driver in the kernel of the Linux virtual machine that instead of using interrupts to process packets coming off the network, does polling. And everybody thinks polling is bad, but not when you're processing millions of packets per second. In that case, you want to poll and then just get huge batches to process and not be interrupted every time something new comes in. And so with DPDK, we're seeing even amazing jumps in performance and latency from what we had before of just the standard networking stacks in the operating system. So I want to show you a quick demo of our accelerated networking at work. So I'm going to come over to this machine here. And I've got several virtual machines set up here in Azure to show you what the world used to look like without accelerated networking, what it looks like with accelerated networking, and then what it looks like with accelerated networking with DPDK. In each case, I've got two virtual machines, a receiver, like this one, and a sender. And each test is going to basically drive the network as quickly as it can for 15 seconds, and then report out what the latency was between the two virtual machines. And so this case you're looking at is non-accelerated standard networking, and you can see the latency is about 190 microseconds. It's not too bad, but it won't look very good when you see what we get with accelerated networking. So here's another virtual machine in Azure with accelerated networking turned on. There's the receiver, here's the sender. And, anybody want to guess? 80? 2, okay. 30, about 30, and that's what we expect, about 30 microseconds. So almost an order of magnitude lower latency than what we get with unaccelerated networking because of those FPGAs and the SDN stack in there. Now let me show you, let me show you what it looks like with DPDK. So here's the DPDK receiver, and here's the DPDK sender. And in about 15 seconds, we're going to see how this does. And yeah. So that is the power of accelerated networking with DPDK in software, what you can achieve. And if you look at that, if you're familiar with network latencies, you're getting down into custom InfiniBand type network performance. Have to remember that this is without RDMA, this is over standard Ethernet inside the data center. And we're going to do better. We're still working on new enhancements to get even better. So that's a look at our accelerated networking. Now let me show you another place where we've been innovating, and that is in trying to connect, or being able to connect virtual machines in two different regions with each other with very high latency, or very low latency, very high bandwidth. That's what I meant. So up to just recently, the way to connect virtual machines in two regions looked very similar to the way you connected a virtual machine to something on premises, through a gateway. You had to create gateways on each side and then send the packets through the gateways. These are software-defined gateways. So they introduced network hops in between them, which caused bandwidth constraints and also introduced significant latency. What we've been rolling out, and now is GA'd in every single region, is global VNET peering. What that means is you can take virtual networks in two different regions, connect them together, and then have those virtual machines directly talk to each other across our dark fiber backbone without going through any software-defined gateways, just purely going over physical hardware in our FPGAs. Now I want to show you an example of what that looks like from a performance perspective. So first, I've got two virtual machines in two virtual networks. I've got this virtual machine here. It's in West US 2 region. And you can see that it's private IP address. So this is not on the internet. The private IP address that's accessible only from another virtual network that would be connected to this virtual network, 10.3.0.5, You can see that it's in the West US VNET in a subnet there. And then you can take a look at our other virtual machine that's in US East. And you can see that it's got a private IP address of 10.0 or 10.2.0.5. It is in the US 2 virtual network in the subnet over there. So let's go take a look at what it looks like to send and receive traffic between those two virtual machines on two different sides of the country. So there's the, oops, I sort of started the receiver first. Let's see if that worked. And here we go. Now watch this number down here, because that's the amount of network bandwidth that we're getting across the country. And let me zoom in so you can see it. Why is it? So we're getting about 20 gigabits per second. So 20 gigabits per second across the United States, because we're not going through any devices, any software-defined devices in between, just a direct connection. And that's the kind of network bandwidth that up until just a year and a half ago or so was very hard to get even within a data center. Now we're delivering it across the United States. So now let's take a look at our servers. Like I said, I was going to take you down a walk. And by the way, there was no applause on that one. Is that just? I think the demos are just so cool, you're like, okay, fine. Really wow us. Okay, so let's take a look at our servers. I mentioned that when I started in Azure, we started with servers that were pretty meager by today's standards, but still pretty decent servers back then. You can see a very tiny font down there. It's 32 gigabits of RAM on this server with a 1 gigabit switch, had hard disks, no SSDs on it, and at the top there, you can see what I've got is a ratio vertically to represent the comparison between RAM on the different servers and the width to represent the cores on each server. Our next generation we had a couple years later, Gen 3 servers. We jumped to 128 gigabytes of RAM, and then we jumped to 10 gigabit switches. So order of magnitude jump in network bandwidth in the servers, significant jump in memory, and then we also started to introduce specialized SKUs, our HPC SKUs. And both of these had SSD, or the Gen 3 had SSDs on it. The HPC SKUs introduced something new, InfiniBand networks, where you can get network latencies between virtual machines in the same cluster of just a few microseconds, so not quite as low, much lower than what we saw even with the DPDK example, by taking advantage of InfiniBand. Great for scientific workloads, MPI workloads that really need tight synchronization between the different servers as they do computing. Our Gen 4 servers there, you can see 192 gigabytes of RAM. We jumped to 40 gigabit networks then, and this was about 3 years ago. We also introduced about 2 years ago this server. We called this Godzilla internally, so I just let you see that we call it that. The reason we call it Godzilla is because at the time, this was a pretty beefy server. It has two 16-core sockets, and it has 512 gigabytes of RAM in it. So the virtual machines that are deployed on this are the G-series virtual machines. And our G5, I think we called it Godzilla just so we could have a virtual machine called G5, for those of you that like private jets. That has about 450 gigabytes of RAM in it. So we considered that was just huge back then. We had the crown for the largest virtual machine in the public cloud. Then here's our Gen 5.1 general purpose SKU. You can see we've moved up to 256 gigabytes of RAM, so half now of what the Godzilla SKU had in it. And we had the FPGAs start to roll out in these. Here's our GPU Gen 5, so we started out roll out GPUs. We got NVIDIA K80s, M60s, V100s, P40s, P4s. So all sorts of GPUs we've got, and more coming. And then we introduced this one recently. So this one we call internally the Beast. And this one, if you take a look at it, it's 4 sockets, 18 cores apiece. They're hyper-threaded, so there's over like 144 cores on it. But the amazing thing about this one, you can see vertically, is that it's got 4 terabytes of RAM in it. And so if you go and deploy one of our M series virtual machines, you're landing on a beast. And I'll just warning, run it for as little time as possible if you want to not spend a lot of money. But it's, the reason we introduced that is for SAP HANA scale-up workloads. SAP HANA workloads are very memory intensive, and so we've got many customers that are running production, including us, SAP workloads on those virtual machines. And then Gen 6, which is coming. And so these have 768 gigabytes of RAM in them, and they still have 40 gigabit networks. We're going to jump to 50 gigabits in the next generation, so this is the last 40 gigabit network. But you can see our general purpose SKUs now that we've got going into our data centers are larger than Godzilla was just 2 years ago. So this is the rate of scale up that we see in the public cloud, which when we originally started was like it's low, cheap commodity servers that scale out. But what we see is very mission critical demanding workloads like SAP HANA demanding a lot more power. What we're building our servers now on is something called Project Olympus. It's an open source server design that we've contributed to the Open Compute project. And we work on this with a bunch of industry partners, both in the silicon and hardware accelerator space. So NVIDIA, Intel, AMD, Qualcomm. We work with all sorts of vendors here to make sure that they support all of these different processor varieties. They can support very high performance GPUs and many GPUs in expanded chassis forms. They can support high density disks and custom designed SSDs that we're making. They can go up to the 50 gigabits networks that are coming. And we're creating, and by the way, this was named one of InfoWorld's Technology of the Years for 2018 recently. This being because it's an open standard, so you can go get servers that are designed to this specification yourself to run in your own data center, and this, we believe, is great for the whole ecosystem. In fact, this design, Gen 6, we designed it in the open. So we contributed our initial design proposal and then got feedback from the community. And then once we got a bunch of feedback in open discussion, locked on the final design, and now we're going to production. Here's an example of one of those high density GPU SKUs you can build with Project Olympus. With NVIDIA GPUs and a custom PCIe fabric that connects 4 chassis with 8 GPUs in each one of them, you can basically have a server with 32 GPUs attached to it with very low latency connections between them, basically as if they're on the same PCIe bus as the server, directly connected to the server. So this is the kind of designs we're looking at now. Obviously, amazing machine for doing deep learning algorithm training. We're also working on high density storage servers. So here's a look at 2 different, on the left side, for hot swap hard disks with shingled magnetic resonance hard disks. So you can see 14 terabytes, very high density drives, which can store, if you put these in a rack, up to 8.6 petabytes in a single rack. And on the right side, you can see an SSD form factor, very high density SSDs, 256 terabytes of NVMe flash in single server. Now, I've talked about FPGAs before, and those FPGAs were in the context of our accelerated infrastructure. We're also applying FPGAs towards machine learning inference. Inference is when you have an input and you want to get a score on it, you want to get a prediction from that input based off of a machine learning model that you've already previously trained. And what we realized is we internally were doing a lot of scoring for our services like Bing, is that the GPUs are just not efficient at doing inference at a very low batch size, we call it. So just basically feeding in 1 query at a time or a few queries at a time, we wouldn't be able to drive high utilization on those GPUs, and we get very high latencies. And so this was, and GPUs burn a lot of energy in our data centers. So we looked at, hey, can we take one of these machine learning models, map it into the FPGA, basically program the FPGA to implement that machine learning model, and then what kind of performance could we get? Because FPGAs are a fraction of the power as a GPU. Plus, we could have the hardware basically optimized for that algorithm. And so that's what inspired Project Brainwave, which we announced this week. This Project Brainwave, you can go take our model, ResNet 50 machine learning image recognition model, custom train it with your own images in Azure Machine Learning, package up the completed model, the augmented model, deploy it to the brainwave service, and what you then have is a custom service endpoint that lands on one of our virtual machines in our data centers that has up to 4 FPGAs on it. Your programming model, your DNN gets programmed into that FPGA, and then you can call that custom endpoint and get back responses. The kinds of responses that we're getting with Project Brainwave is about 1.8 milliseconds per query, and that's with a batch size of 1, meaning you can send it 1 query at a time and you get that kind of latency. And you can drive throughputs that are comparable to a batch-oriented device like a GPU at the same time. So you get very high throughput, very low latency for a fraction of the power as a GPU. Now, one of the projects that we've been working on is something called AI for Earth. So we've been working with the Chesapeake Conservancy, as well as Esri, on taking maps of the whole United States and classifying blocks of the maps to determine what kind of land it is. Something very important for conserving the natural ecosystem, for looking at the effects of global warming. And up to this point, the process of doing this kind of analysis has been very manual. Images come in from the satellites. Humans are then saying, oh, this looks like forest, this looks like urban. And by leveraging Azure Machine Learning with Brainwave, we're able to do some amazing things. I want to show you a quick demo comparing what we see with Brainwave. And I've got to unlock this. Oh, it's a pin. This is Hashi, by the way. Say hi, Hashi. So here's AI for Earth. So what you're going to see when I click on the CPU button is you're going to see the number of images scored per second, sending 1 image at a time to the CPU. And the rate is about 6 images per second. If we switch to a GPU, you can see, by the way, there's multiple images in each one of those squares. And so we're getting about 60 images scored per second off of the GPU, which is about an order of magnitude better than on the CPU. But when we do it on the FPGA, you can see that it pretty much outstrips by almost an order of magnitude. And so the entire United States is about 195 terabytes of imagery. We have taken 800 FPGAs from our Brainwave cluster and scored the whole thing in less than 10 minutes. And it's about 23%, right now it's in preview, it's about 23 cents per million images scored. So it's extremely economical as well. And one of the great aspects of this is you get a great economy, plus you get great performance, and you don't have to batch your queries. So if you're a web service with the images coming in from all over the place, you don't have to sit there and wait for a collection of 128, which is what's kind of the sweet spot for GPUs to gather before you go score them, and then impact your latency at the same time, both because the GPU is higher latency and because you're also batching. Here, you just feed it in as they come. So let's talk a little bit about Azure Compute now. And Azure Compute, just like Network, you can see has Azure Resource Manager, has some resource providers. I'm going to focus on the container aspects here because, of course, it supports virtual machines, but you've seen in the keynote demos on Monday and some of the other sessions, Azure Kubernetes Service, new name for it, is one of those resource providers that creates Kubernetes clusters. We also have our own microservices platform called Service Fabric, which has its own resource provider. And we've got an announcement this week that I'm going to show you in a second, but take you a little bit deeper into the architecture so you can see, just like in software-defined networking, we split it into the management APIs, the controllers, and then the data plane itself down on the servers. And this is, so we're going to sit and study this for a little bit. Just let me know when you're done. I'm just kidding. This is the kind of complex flows that we have when you deploy a virtual machine. So the compute resource provider goes and makes network requests to the network resource provider. That talks to a regional network manager, which talks to a tenant manager down there on the left, and you can see that a big dance happens across our architecture when you go deploy a virtual machine. But the announcement that we've got this week is something called Service Fabric Mesh. Internally, it's project code named Seabreeze. The idea here is, if you're familiar with Service Fabric, it's a microservices platform. You can create microservices made out of just vanilla containers. You can use programming models like the actor programming model. You can create stateful services with the reliable collections programming models. And what we've done is simplify the management of Service Fabric applications. To this point, the first step, just like with any orchestrator you've had to perform, is go stand up the orchestrator first. Go provision the virtual machines and add them to your cluster. And then typically you've had to do some management of those virtual machines. We're taking all that away and making it so that you can simply take a Service Fabric application. Sorry, here's a look at the architecture inside. Take a Service Fabric application, hand it to us, and we'll go, it's containerized, we'll go and stand up those containers ourselves, honoring placement constraints, no infrastructure to set up auto-scaling rules, so no virtual machines to worry about, just your application. Completely serverless microservices. So I've got a quick demo of that in action. And what I'm going to do is go, actually, getting lost in my demo machines. That one is, I think it's, no. That one is not, oh, it's over here. No, it's not there. It's over here.
No, I come back so much, they gave me a mic.
Oh, okay, great. Thanks, Hashi. You see, so where's this one again?
I think it got disconnected.
Oh, it got disconnected, no wonder. All right, so you connect it again.
All right.
It looks like it got a Windows update. So it's even better than before. I hope we got the new notepad.
You're right.
All right.
Thank you.
So, yeah, thanks, Hashi. So what we got here is Visual Studio, and if you go say New, Project, oh, you can't see? Sorry. Oh, no wonder you didn't see what was going on there. That was probably better. So here we go. Here's Visual Studio. And what I did is create new project. And now we're waiting for that new project dialog to come up. But one of the things you're going to see there is new Service Fabric project, or Service Mesh project, rather. Or not. Oh, there we go. So you can see there's a new one, Service Fabric Mesh application here. That's a serverless Service Fabric application. That is a simplified version of the Service Fabric app model. You can see I'm going to create an ASP.NET Core app here. And what this is going to do is just create the generic ASP.NET Core web app for us. We can start to fill in. And one of the things you can do is launch this, just like Service Fabric standalone, launch this in your own cluster on your machine. So it supports a fully simulated multi-node cluster that you can do your own debugging on right here in your desktop. So if we go to debug, run, what this is going to do is fire up a simulated Service Fabric cluster here and then launch the web app in a container onto this, and it's going to open up the browser. This is the way that you would do debugging for your Service Mesh application. Now let's say that you want to go deploy it into production or into the cloud to go do some testing on it. What you would do at that point is come up into, can't reach the page, you would come up here. Oh, the Service Fabric, okay, so sorry. What we're looking at here is Service Fabric application that I've got over here. This is the local cluster. It hasn't finished coming up yet because of that reboot, so it wasn't running. But here we've got Azure's portal, and I've already deployed a service mesh application to Azure. This is coming out in preview in just a few weeks. But you can see here we've got basically the only resources you've got now are the network for the application and the application itself. And what I'm going to do is open up Cloud Shell. I'm going to get the IP address for this thing. And we're just going to, oh, it's actually lost from my command history because of the reboot, so I don't think I'll be able to recreate this command for the demo. But, oh, yep, there it goes. So this is the public IP address of that application. And you can see basically I said show resource group for that mesh application. And I hit it, and there it is in Azure. I did not stand up any Service Fabric cluster to get that app going. Basically, I did a publish from Visual Studio of that app that I was just showing you me creating in a few seconds on the desktop. What we'd see down in the browser at this point probably is that same app launched on the local environment. But the point is that this is the full richness of Service Fabric. So Service Fabric, for those not of you familiar with it, supports Windows, Linux, Java, .NET, actor programming models, stateful services, reliable collections, and all of that is supported on Seabreeze as in a serverless form. And you can take those applications, you can run them on standalone Service Fabric clusters that might be in other clouds or on-prem or in other places. Let's go take a look at what those other places might be. Now, as you heard in the vision, the world is a computer, and one aspect of that vision from an infrastructure perspective is taking all the programming models, all the infrastructure, the microservices that you design and develop for the cloud, and trying to support them as far down the device spectrum as we can, down to the edge, which would be your MCUs, your Azure Sphere type devices that are very tiny. Now, everything can't necessarily go down that far because of limitations and resources as you get down into smaller devices. But down when you get, if you're talking about Raspberry Pi, Arduino type class edge devices, you can do a lot of pretty rich things on them. And there's no point in having a different microservices programming model for the cloud and another one for the edge. We want that experience to be as consistent as possible so you can take those apps and run them on the app, on the cloud or on the edge, depending on where's the best place to run them, where they need to run. One way that we're enabling that is by having IoT Hub be a place that can control the deployment of orchestrators, the bootstrap of orchestrators on the edge, and then have the orchestrators in the cloud be able to manage the lifecycle of applications on those edge devices. What I've got here is one example topology with Service Fabric, where IoT Hub, where you can, in this world that's coming very soon, you'll be able to create an Azure Resource Manager template that fully describes an IoT application, including IoT Hub, the IoT provisioning service, your backend services, your Azure Stream Analytics and HD Insights, as well as your Service Fabric application that might run on the back end, and a Service Fabric application that runs on the edge, down on these small devices. And with the combination of Service Fabric's resource provider in the cloud and IoT Hub in the cloud, they orchestrate the deployment of those apps down on those devices automatically without you having to go set up clusters and manage them on the edge devices. Now I've got a demo here I'm going to show you of this in action because I want to highlight one aspect of this, and that is that because it's Service Fabric, it supports stateful services. And more, you're going to have scenarios where you need to support high availability and or support state for disconnected scenarios. So what I've got here is, first I'm going to show you IoT Hub in the cloud, and I've got 3 edge devices here that I'm going to connect together to create a cluster. So I'm going to create a service edge cluster here. And then you can see what happens is this shows up as an edge cluster device. So those 3 devices. Now let me take and show you what that looks like in a real-world demo. So I've got 3 devices up here. They're IoT core devices. They're running Service Fabric, stateful application with high availability on the edge. And to set this up, I thought I'd make it interesting. So how many of you have seen Die Hard? So quite a few of you. This is the Die Hard scenario. So the building, you can see it's Nakatomi Tower. We've got 3 floors here simulated. Each floor has one of these devices on it. And Bruce Willis is in the building, and he wants to set a fire to lure the bad guys, distract the bad guys. So here he's going to, well, first, the bad guys, what they've done is disconnected the network. And so I think I'm doing the right wire here. Yes? Yeah? Okay, so this is the right wire. It's the bad guy, there's the wire. So you can see that these are on the local network here connected directly to these devices. So we can still see them pumping telemetry, although they're not showing up in the cloud. This is operating completely autonomously at this point. And now Bruce Willis, so yippee-ki-yay, I think there's something that comes after that, but I can't remember what it is. And you can see that the fire starts, and in a second, we should see, oh, the fire alarm has gone off with the rule that has been sent down to the devices to say, set off the fire alarm when the temperature gets above a certain threshold. So now, the bad guys are like, let's turn off the fire alarm because the fire department's coming. The fire alarm is going off on floor 35. So I'm going to take floor 35 and unplug the power. So these are labeled here. And then, oh, we had a failover now to floor 34, and the alarm went back on. So that is because Service Fabric is operating this cluster across these, that fire alarm app running in a container has just failed over from one of these devices to another, and the bad guys are going to get caught because the police and fire department are on their way. So that is a look at that. Now, one of the things I want to talk about is data sensitive. We're good there. Thanks. One of the things I want to talk about is data concerns with the cloud. So a lot of customers are comfortable having their data move up to the cloud now because the cloud, in many ways, is more secure than on-premise infrastructures. But there's still some data that is extremely sensitive and that customers wish they would have more control over than the cloud can currently provide. Those threats include having a privileged admin. Maybe they're concerned with an insider going after their data, or a hacker breaking into the infrastructure, or a third party coming and asking for their data without their consent. And so we've been working on something called data encryption in use over on the right side, based off of something called trusted execution environments, or TEEs. And what a TEE is an isolated piece of the operating environment on a server that can't be accessed from outside it. You can have different providers, so a couple that are in production now, virtual secure mode, virtualization-based security that's part of Server 2016, and software guard extensions from Intel, which is processor-enforced encryption in use, meaning that no unencrypted data from inside one of these enclaves, a TEE enclave, ever leaves the processor complex. And it's protected from access from outside because of the rules in place. These enclaves can attest or can produce assertions from the processor as to what code they're running inside them. And that way you can establish trust with that piece of code and know that it's okay to release your secrets to it so that it can decrypt data in the cloud and process it without risk of those kinds of problems I just described. I'm excited to announce that today we had first announced a very limited preview of this back in September, and we've been working hard with Intel to bring out a new expanded preview with the latest SGX processors into our cloud, the Melo processors. And now we've expanded the preview, and we've got a bunch of different aspects of this that we've started to flesh in that you can get access to now as part of this preview, including a SDK that lets you program to the enclave with tools like Visual Studio. We're also working on lighting up really cool scenarios with this. One of them that I'm going to talk about here is one that's got a lot of people really excited, and that is combining different data sets for machine learning. One of the classic cases that we see when it comes to machine learning in the cloud is different healthcare providers that have their own data sets but cannot or are unwilling, because they want to protect the privacy of their own patients, to share that data with other healthcare providers so that they can do machine learning on the combined data set and maybe get deeper insights by getting correlation, getting features from different aspects of the patient population. With confidential computing, they can securely share their data with an enclave that they trust the algorithm inside not to leak their data, and then get those machine learning insights from it. And so I want to show you a quick demo of that in action. And that is on machine number 6. And it looks like I've lost, oh. To prove to you it's not a, that's really the network. That wasn't part of the demo script. So this should reconnect here in a second. And then what I'm going to show you is, okay, and that one is over, not on here. All right, I might have to ask Hashi where this one moved to. Hold on.
Here I am again.
Where's that one go?
I think it's on this machine. We have so many demos now. I myself is confused.
Oh, there we go.
Yeah, this is redundancy, people.
Yeah. All right, so what I'm going to do is launch the server. And this server is what's going to be running the machine learning model. And now we want 2 hospitals to share their data with that server so that they can get insights out of it. Here's hospital A. Here's hospital B. And here you're going to see hospital A's plain text data, the data that they're feeding into the model, the different features that they've got from their own data set. What they're going to do now is encrypt that data to a key that they're going to make available to that enclave running on that machine learning server in a second. So now this is what that encrypted data looks like in encrypted form. And then what we're going to do now is send that data to the server to process it. And for hospital B, we're going to send it to, oh, something happened out of sync here. Oh, I know what happened. There we go. Now, what this is going to do is it trains the model, and here are the model parameters. Encrypted form, it was sent back to the hospitals, though. And so here are the parameters for that model in unencrypted form. All of that done without that data ever leaving that SGX enclave in that server there where the machine learning model was trained. Both hospitals know that their data was never exposed to anybody else except for that machine learning trainer right there in that server because of the power of SGX. So they did their confidential computing in the cloud. Their data, patient data, is secure, and yet they're able to get that combined insights from that data to better serve their patients. Now they can take that model now and run it on-prem and get their predictions from it using that combined learning. Okay. Now, Azure Storage has a topology that is basically a 3-tier, just like you saw before, when it comes to the data architecture. So there's front ends, there's middle tiers, partition servers on the back ends, and then there's disks. And one of the things that that's coming that I think many of you that interact with Azure Storage will be very excited about is that we're blowing the limits off of blobs and off of storage accounts. So if you take a look, a storage account today has a limit of throughput of about 50 gigabits per second. A block blob today has a limit of 60 megabytes per second. With this high throughput block blob architecture you can see here, which scales out the blob across many different servers, you can drive up to the maximum throughput of a storage account off of a single blob. And there's no warm-up required. You just get that amount of bandwidth as you hit the blob. So just to give you an example of the performance improvement, a 5 terabyte blob you can upload in 14 minutes, which used to take 12 hours. So that's the kind of performance enhancement. So I'm running a little bit behind time, so I'm going to skip some of this stuff and jump to DNA storage, which I think is kind of cool. The slide I skipped, by the way, is about Project Silica, which is storing data in glass, and that's something I talked about at Ignite last year. I also talked about this, but this one I think is worth covering here for a second. That is encoding data in nucleotides and sequencing them into DNA and then storing it, which sounds pretty crazy, but we've got a project going with the University of Washington here. This is 1,000 times denser than tape. It lasts 2,000 years in the right conditions. And with that 1,000-time density, you'll see just what kind of storage you can fit into a very small space. But the way this works is you take the binary data, you encode it into nucleotides, AGCT, you synthesize a DNA molecule with the sequence, and then when you want to go read the data, you sequence it just like gene sequencing works today, and you read back that data. Here's, in this tip of this, there's equivalent of 10 terabytes of data in the very tip of that little filament there. And when you put that in a rack, and here's a picture of one of the devices that stores the DNA, that rack will be able to store 1 zettabyte of data. 1 zettabyte. So you've got gigabytes, terabytes, petabytes, exabytes, and zettabytes. So we're talking, and by the way, the amount of data in the world right now is about 20 zettabytes. So 20 of these racks, and we can store it all. So I want to show you quickly the little look at the Azure operating system and what it looks like inside, and it's very kind of generic. Hyper-V, Windows Server 2016, server core, there in the host partition, serving virtual machines. We try to keep everything out of there that we don't absolutely need to minimize the security footprint and the servicing footprint. But otherwise, it's the same software you can run yourselves. Now, we have added some enhancements to it for the cloud. And these enhancements we've added over time to improve our ability to roll out patches to the hypervisor and to the virtualization stack without causing impact to customer VMs, without causing any downtime. And you can see a bunch of technologies here. As you start at the bottom, it's called Virtual Machine Preserving Host Update. The way that works is that we freeze the virtual machines in RAM, we reboot the operating system with a new version underneath it, and then we resume the virtual machines. And the blackout times that we're at right now is about 15 seconds for that. We're driving down to below 10 seconds. But then there's these other versions of that where you freeze the virtual machine and update just parts of the operating system in the virtualization stack and cause less downtime. I'm going to show you 2 of those. One of them is we call VMFoo Ultralight. And this one, you can update everything except for one small piece of the virtualization stack in the hypervisor. Anything else on the server, you can update. So those 2 pieces of software are the only things that can't be updated here. And what makes this really cool is that this works independently of how big the server is. And let me show you an example of that over on number 7. Okay. Hashi's going to get sick of coming out here. But I think this one is what he wrote down his password for me, so, which I'm going to have to talk to him later about that. So you can see I've got this is a GPU virtual machine in Azure. It's got 4 Tesla M80 GPUs. It's got it's got a bunch of RAM on it. I think 256 gig of RAM on it. So it's a beefy server. And what I'm going to do, I've got a patch for the virtualization stack, a piece of it that's absolutely required for that virtual machine to be running. It's called Store VSP. It's a driver. And what I'm going to do and watch very carefully because this is running a graphics benchmarking app, I'm going to patch that driver. And what that means is I'm going to freeze the virtual machine, unload the virtualization stack, and reload it with that updated driver. Done. You can see I went from Friday store VSP to Saturday's version of store VSP. And then I want to show you one other demo, and that is our ability to, that's the wrong one, our ability to apply patches to the hypervisor itself using hot patching. This is brand new technology that we've just worked on. By the way, we've rolled out through using hot patching in other parts of the virtualization stack about 50 times over the last year or so. So no impact to customers at all, basically, and you're going to see that right here. You can see we've introduced a synthetic bug into the hypervisor where the CPU ID command takes a long time. It takes a millisecond. It should just be taking a few microseconds. And what I'm going to do is apply a hot patch that fixes that bug by pressing enter, and watch the latencies on that there, boom. So that is hot patching, and we continue to work on these technologies to make them even more applicable and lower blackouts and lower brownouts and just try to keep our VMs running nonstop, even in the face of security and reliability and functionality updates. Now I've got one last section before I let you go, and that is quantum computing. So you might have heard that we've been working on quantum computing. We've been talking about it for about a year now publicly, and the reason that we're investing a huge amount of money in this. This is kind of a moonshot project for us, but not a moonshot in the way that a moonshot's unrealistic, but a moonshot in the way that we think that this is on the verge of being real and practical. And the way we're getting ready for it in a bunch of different ways to make it available in Azure. And the reason that quantum, or the applications that can be addressed with quantum computing, environmental sciences, material science, coming up with new medicines, coming up with doing machine learning algorithms. And the reason that quantum is so appealing to these kinds of algorithms is some problems, if you simulated them on classical computers to solve them, you get exponential scaling of the amount of data required to represent the state of the simulation, the state of the algorithm. And effectively, it's like in classical computing, you're basically doing probes for a solution, searching for the answer. And you're doing it in a very slow way with a huge amount of memory consumption. When you do it with quantum computing, you basically, oh, there's a nice animation here. Let me get back to that. There. It's basically searching the whole space for an optima. And it does this in a few seconds, where in classical computer, the same algorithm, the same approach, the same problem would take thousands of years to come to that same optimal solution. So that's why it's so appealing. Literally can solve problems that are just impossible to solve efficiently in classical computers. Now this requires a massive effort, and that effort includes hardware engineering. Lots of hardware engineering. This shows you an idea of what we're working on. You can see that in the middle is a temperature scale in Fahrenheit for those people that are more comfortable with Fahrenheit, and in Kelvin for people familiar with the scientific scale, where 0 is absolutely nothing, 0, no energy at all. To give you an idea of where we have to operate these quantum computers, because they have to be kept in a noise-free environment, meaning no electromagnetic interference, no particle interference, to keep them stable, these particles, the qubits they're called. We've got to operate the quantum computer at about 0.4 degrees Kelvin. Deep space, the heart of deep space, is about a little over, it's between 2 and 3 degrees Kelvin. So this is significantly lower than the coldest of cold deep space. Then, to control the quantum computer, we can't control it from standard hardware because that's just too incompatible. The temperature differences, the speed differences are too high. So we've got to create a cryogenic computer to control the quantum computer that operates at about negative 453 degrees Kelvin. That is cooled with liquid helium. And then for the memory systems of the computer to store the data that feeds the quantum computer, those can be run a little bit warmer at about 77 degrees Celsius, or Kelvin, sorry, 77 degrees Kelvin, which is where DRAM, where the DRAM operates. And so you can see over here on the left side, there's a quantum chip there at the top that we've got a prototype of working. Here's the new types of memory technology we're creating, these memory bands there in the middle. And then that's the quantum computer under electron microscope there at the bottom. It's the first time I think we've shown these publicly, these pictures. The key to this, by the way, that makes our approach different is that we're working on something called a topological qubit. If you compare what we're doing with the qubits of the other approaches, ours, you can see are 3 to 4 orders of magnitude more stable, and that means that we can create quantum computers that are vastly larger and run them stably and come up with good answers. So we can run computers with thousands of qubits, where the other types of qubits require many more just to error correct. We're on the verge, we think, of creating this topological qubit. In fact, we think we actually created it. It's called a Major-Anna fermion-based topological qubit. We think we've made it, but when we look at it, it disappears. So we're not sure. Now, we've also created something called the Quantum Development SDK, which you can download for free from Mac and Windows and Linux. And I'm going to show you a very last quick demo of that thing in action. And that is here. And so I've got a little algorithm here that consists of a C# program that drives the Q# program. The Q# program here is something that says, it's called super dense encoding, where you can quantum entangle 2 qubits, send one to one place, send one to the other place, then encode one of the qubits with 2 classical bits of information, and then read the other qubit, and it reads those 2 bits of information. So this is like kind of teleporting information from one place to another place, and 2 bits of information. So I'm going to show you that in action with a little demo with a host process, just show you what it looks like to run this as a real app in the simulator. And this is using a quantum simulator here on the local laptop. You can simulate about, I think about 40 qubits here on a laptop like this. If you need access to more qubits, you can get the Azure Quantum Simulator. Now the web server is running, and I'm going to run UAP app here. Okay. Maybe, there we go. So super dense encoding is kind of like teleportation. So this program is going to call that Q# algorithm to do that transmission of classical information from one qubit to another. You get to pick who you want to send. And that's the encoding that we're going to send. So yell out your favorite Star Trek character. Spock. All right, here we go.
Energize.
And there we go. That's it. That's we just teleported using Q#. And with that, I want to thank you very much. Hope you had a great session.